Hey, what's up, Mr. Sutter here. Today we're going to be talking about electrical circuits. Let's get started. All right, so before we talk about circuits, we need to talk about a few electrical variables. Now, there are three variables that are important to note when discussing electrical circuits. They are voltage, measured in volts, resistance, measured in ohms, and current, measured in amps. On this picture on the right, we can see a little illustration of these three variables interacting with each other. The voltage pushes along the current, which is trying to move through the wire, and the resistance is trying to stop the movement of the current measured in amps. Right? Let's take a look at those variables a little bit more in depth. Right. So first, we're going to look at voltage. Voltage is the measure of energy given to the charge flowing in a circuit. The greater the voltage, the greater the force or pressure that drives the charge through the circuit. A voltmeter is a device that measures the voltage in a circuit but does not supply a voltage itself. Here are some sources of voltage. On the left, we have a D-cell battery, that's 1.5 volts. In the middle, we have a 9-volt battery, which you're probably familiar with. And on the right, we have an outlet, which is 120 volts, which is the standard voltage for outlets in the United States. Right? These are all sources of voltage. And next, we have resistance. Resistance is the opposition to the flow of an electric current, and it produces heat. The hotter something becomes, the harder that it is for the current to flow through. Again, the greater the resistance, the less current that gets through. Good conductors have a low resistance, and resistance is measured in ohms. And again, we see here the voltage is trying to push the current along, and the resistance is what's squeezing the current, making it harder for the current to get through. All right, so what influences resistance? The material of the wire, aluminum, copper have a low resistance. Thickness, the thicker the wire is, the lower the resistance is. The length, the shorter the wire is, the lower the resistance. And the temperature, the lower the temperature, the lower the resistance. So high temperatures have high resistance and low temperatures have low resistance. So ideally, if you're building a circuit and you want the current to flow through as fast as possible, you're going to want a metal wire, perhaps made of aluminum or copper. You're going to want it to be very thick, right? You're going to want it to be very short, and you're going to want it to be cool. You want it to have a low temperature. So in total, if you want a really low resistance, you want a metal wire that's very thick, short, and cool. The opposite would be one with very high resistance would be a wire maybe not made of metal, but it could be made of metal that was very thin, very long, and already very hot. All right, lastly, we have current here. So current is the flow of electrons from one place to another. Current is measured in amperes or amps. You might be familiar, that's the same thing we were talking about the guitars and amps. That's current. Right, now current is an example of electrical kinetic energy, moving electrical energy. Right, so how can we control currents? With circuits. Right, so a circuit is a path for the flow of electrons. In real life, when we're trying to control the current of traffic, we're trying to control the flow of cars, we make a roundabout, right? When we're trying to control the current in a circuit, we use wires. All right, so here's a simple electrical circuit. I have a few different things here. I have a bulb, I have a battery, I have a switch, and then wires which connect them all. Right now the switch is in the open position. If I click the switch, now the switch is closed, and the electricity can flow from the battery through the switch, through the bulb, and then back to the battery, right? If I open the switch, it turns off. If I close the switch, it turns on. If I open the switch, it turns off. If I close the switch, it turns on. So a circuit is only complete, that means working, when the switch is closed because there's no break in the wire. If I open the switch, the electricity is not running not running from the battery through the switch to the bulb, so it doesn't turn on. When I close the switch, electricity can move through the entire circuit in that big square shape. All right, so what types of materials can circuits be made from? So in order for a material to carry a current, it must be a conductor. Engineers perform lots of tests for conductivity. Conductivity is the ability to conduct electricity. So the engineers, they perform lots of tests for conductivity when they're choosing a material for building a circuit. And some liquid solutions can even be conductors. So on the left, we have ethanol, which has no conductivity. So you see the light bulb does not turn on. In the middle, we have potassium chloride, which has a very high conductivity, which you see the light bulb lights up all the way. And on the right, we have acetic acid, which has a low conductivity, so the light bulb turns on a little bit, but it doesn't become fully bright like the one in the middle. Right? All metals conduct electricity, but some are better than others. Engineers test materials to see which ones are best for the job they're trying to perform. So on the right, we have what looks like a piece of an elbow of a copper pipe, and they're trying to test to see the conductivity of that copper piece. Right, so let's look at some common electrical symbols. This symbol right here with that line with the little bump on it is a bulb. This symbol here with this rectangle on the line is a battery. This is a on switch. You can see where the two pieces are being connected by this metal wire. This is an open switch. You see how they're not touching. And lastly, this black piece is a wire. Right. In a simple electrical circuit, again, if the switch is closed, the light bulb turns on. If the switch is open, the light bulb is off. So right now my switch is open, so the light bulb is off. I close the switch and the light bulb turns on. I open the switch, turns off. I close the switch, it turns on. I open the switch, it turns off. I close the switch, it turns on. Now there are two types of simple electrical circuits. We have series circuits and parallel circuits. Let's look at those. Right, so our first type here is a series circuit. In a series circuit, the components are all lined up along one path. If the circuit is broken, all the components are off. So you can think series like a series of books like Harry Potter, right? So in a series of books, one comes after the other. One book, two book, three book. In a series circuit, the light bulbs come one after another in the same row. One bulb, two bulb, three bulb, right? If one of these bulbs break, then all of the bulbs don't work anymore. This is like when you have an old set of Christmas lights and one light breaks and the rest of them don't work. That's because they're lined up in series. If one breaks, it means the electricity can't flow through all of them. So I close the switch, all the light bulbs turn on. If I open the switch, all the light bulb turns off. I close the switch and they turn all on again, right? Let's move on to parallel circuits. Right, so in a parallel circuit, different parts of the circuit are on separate branches. If the circuit is broken at any one branch, all the components on that branch will turn off. But all of the components which are not on that branch will stay on. This is why a parallel Christmas tree lights wired in parallel are better than Christmas tree lights wired in series, because if one light breaks, all the other lights still stay on. So if I close the switch here, all the light bulbs stay on. If I open the switch, all of them turn off. So let's leave them turned on. So if I were to break this light bulb here, all of these other light bulbs would still work, because even if I break this one here, the electricity can still go through this path, it could go through this path, or it could go through this path. Similarly, if I break both of these, the electricity can still go through this path, it can still go through all the way around this path. If I break all three bulbs in the middle, the electricity can still go around in this path. But if I open the switch, none of them will turn on, right? That's going to wrap it up for electrical circuits. Thanks for watching. I hope you learned something, and I'll see you in the next video.